and start. So today we're going to be going over solutions and general rules regarding solutions and solubility. So first of all, we have to understand First of all, we have to understand whether or not something is soluble in something else depends upon its polarity. So the principle for solubility is light dissolves light. What that means is that if you have a polar solvent, it'll dissolve a polar solute. If you have a nonpolar solvent, it'll dissolve a nonpolar solute. But a nonpolar solvent cannot dissolve a polar solute, and a polar solvent cannot dissolve a nonpolar solute. So, let's take a look at some example problems here. Firstly, you have NaCl, and actually, you have two solvents, water, and you have CCl4. Now, CCl4 is a nonpolar solvent. You might also see something like hexane given. And I don't know particularly if your teacher is going to give you that these are polar or non-polar. You may have to know that. Although water, it's pretty easy that you should know that that's polar. But with the other ones like CCl4,
or hexane or methane or something like that, or non-polar.
Yeah, if you have a carbon compound where carbon is bonded to all the same outer atoms like CH4 or CCl4 or CBr4, those are all going to be polar. Those are all going to be very polar. Or non-polar, sorry. They're all going to be non-polar.
Yeah.
Or if you have a compound that's composed of just carbon and hydrogen, like hexane, then it's C6H14 or something like that, that's going to be non-polar as well. So any hydrocarbon or any compound where the carbon is bonded to the same outer atoms, that's going to be polar. I mean non-polar, sorry. Keep on saying polar. It's going to be non-polar. It's going to be non-polar. Alright. So looking at the first substance here, NaCl. NaCl is ionic or covalent?
It's ionic.
Ionic. And any ionic compound will automatically be very polar. Exactly. So this will be soluble in water. But it will be insoluble, which means not soluble, insoluble in CCl4. And then I2, is that polar or non-polar?
It's a polar.
Actually, no. Any element that is bonded only to itself?
To itself is a non-polar.
I2, N2, Cl2, any of those guys are going to be non-polar. Now because that's non-polar, because this is going to be non-polar, this would actually be insoluble in water, but soluble in cyclohexane. And then we can look at something like olive oil. Or really any kind of oil.
Any kind of oil is non-polar.
Yeah, an oil is going to be a non-polar substance. An oil is going to be non-polar. And so that is going to not be soluble in water. That'll be insoluble in water. But it will be soluble in something like carbon tetrachloride. Now, last but not least, we have sucrose. Sucrose is table sugar.
Yes.
Is that going to be soluble, or is that going to be soluble or insoluble in water? Soluble. Which means that
it's polar.
Yeah, it's polar. And insoluble in this. Now, if you had any sort of alcohol, alcohols will tend to be soluble in water.
Yes.
Because alcohols also have hydrogen bonding. So typically speaking, if you have any CH3, NH2, any carbon nitrogen compound, or CH3 OH, carbon compound that also has oxygen and OH in it, these are going to tend to be polar. And in fact, the more oxygens and the more nitrogens that are present in a carbon compound, the more polar they tend to be. Only exception being, of course, CO2, because
CO2 is
non-polar. Yeah. Because CO2 it's like this in the sense that it is carbon only bonded to one other type of atom. But in this case, carbon's bonded to more than one type of atom. It's bonded to hydrogen and oxygen. And when it's bonded to hydrogen and oxygen, or even more than one type of atom, the molecule tends to be polar. Okay, good. Well, I think we beat that horse to death. Let's go to the next topic.
I didn't know that carbon and nitrogen is polar. I didn't know that.
Oh, really?
Any kind of carbon and nitrogen is polar. I didn't know.
Well, it's when carbon is bonded to more than one atom, especially if one of those atoms is nitrogen or oxygen, then that'll make it polar. All right, so now the next question says, at 22 degrees Celsius, the solubility of KNO3 is 34 grams per 100 milliliters of water. If a solution contains 66.4 grams of KNO3 dissolved in 187 milliliters of water at 22 degrees Celsius, is the solution saturated or unsaturated? And if saturated, how much of the solute remains undissolved? So whenever you're given a solubility like this,
I think that is unsaturated.
well, whenever you're given a solubility here, you want to make sure that you write the solubility as a fraction. 34 grams of KNO3 over 100 milliliters of water, right? That's the solubility that's given. The given solubility should be your, shall we say, starting fraction. You then want to set up a related fraction to figure out how much could dissolve in the given amount of solvent. How much solvent is given?
187?
Yeah. 187 milliliters of water
At the bottom?
given. Now it says you've added 66.4 grams of KNO3, but I'm not going to put the 66.4 grams up here. I'm not going to put that. What I want to do is I want to figure out how much can dissolve in 187. So I will put that as an X here, and then I can cross multiply and solve for this. So it'll be essentially 100 times X is equal to 34 times 187. And what's 34 times 187?
$63.58.
Well, it's 6358 would be this times this, right?
No.
But then then you divide both sides by 100, and you do get.
I did all of it.
You did it all together, yeah. That's 63.58. Now, of course, you only have two sig figs, so technically speaking, this would really round.
So 268 is 64.
64, yeah. 64 grams. Oh, let's keep an extra sig fig though. For now. 63.6. But this is where your significant figure stops. You only have two sig figs. Because remember, you're not actually supposed to round until the very end of a calculation.
Okay.
And we're not really done with our calculations yet. Because so now that we see that this is the amount that can dissolve, this is the amount of KNO3 that can dissolve, how much did we put into the 187?
So we have 34 there, but the maximum amount that we can dissolve is 63.
So is it saturated or unsaturated?
Or it is unsaturated.
Oh no.
No, dissolved. Yeah, dissolved, because 34 dissolved completely in 63.
Well, no. Because remember, this is how much can dissolve. This is how much is capable of dissolving. How much did we add? Well, we added 66.4.
Oh, okay, I didn't pay attention to 60, but I just paid attention to 34.
No, the 34 is just the solubility.
Okay, I got you.
Yeah.
Yeah.
It says if the solution contains
So
60.
whenever you have 64, this is undissolved, so it is saturated.
Yeah, this is saturated because only 64 grams or 63.6 grams can dissolve, but we've added more than that.
Yes.
And so there's some that's not going to dissolve. How much is going to remain undissolved?
Almost 3 point, I think maybe 2 point something. We have to subtract 66 minus 63.
Yep. Now technically speaking, we only have this many sig figs. So when I do subtract that, I do get 2.8 grams. But since that's my last significant figure, that means this is going to be 3 grams undissolved with appropriate significant figures.
Yes.
Does that make sense?
Mm-hmm.
Cool.
I didn't pay attention to the second number, 66, or I just look at the 34 grams.
Yeah. These problems really do require you to be very, very careful at looking at the question to make sure that you read it properly to know what the different amounts are telling you. Alright, so now, question number 6 says, if enough sodium nitrate is dissolved in 456 milliliters of water to make a saturated solution at 25 degrees, how much more sodium nitrate must be added to make the solution saturated at 60 degrees? So, we know that enough is added to make it saturated at 25 degrees. So we can solve for that. Solve for how much it is needed to make it saturated at 25 degrees. And it says at 25 degrees, the solubility, according to that little table there, is 90 grams sodium nitrate for 100 grams of water. But we don't have 100 grams of water. How much do we have?
Here we have 453 milliliters.
Yeah, and you know, fortunately, milliliters and grams are the same thing for water because water has a density of 1. So the milliliters and grams are the same. So the 456 milliliters can also be written as 456 grams of water. And so we have to solve for how much is dissolved in 456 grams. Unfortunately, then it means we're just going to take 90 times 456 divided by 100.
41040 is the multiplication. And divide 100. 41040.
Yeah, is equal to 100x. When you divide by 100?
Is 410.
Exactly. 410 with the decimal. Well, no, I guess.
Yes, 410.4.
Yeah, and we'll keep the sig figs for now, but we really only have probably 2. 410.4 grams of sodium nitrate. This is how much can. This is how much is dissolved in a saturated solution at 25 degrees. Now we increase the temperature at 60 degrees. And so what we're going to do here is we're going to basically do the same type of calculation or conversion, but we're going to use the solubility at 60 degrees to figure out how much would be needed to make it saturated there. And the solubility at 60 degrees is 125 grams of sodium nitrate over 100 grams of water is equal to X over 456 grams of water. Because the amount of water is still the same in both cases. The only thing you're doing is you're warming it up.
So multiplication is 4.
So you can just do the same cross multiplication you did before.
57,000.
57,000. And then that's equal to 100x.
Divide 100.
Divided by 100.
570.
Yep. X equals 570 grams of NaNO3. So 570 is the amount that you would need. 570 is the amount that you would need to have a saturated solution at 60. This is the amount in a saturated solution at 25. So how much more grams of NaNO3 would you have to add to this to make it saturated at 60 degrees Celsius?
To 60. So if you want to 60, we have to count subtraction.
Yeah.
And
Subtract the amount that you need at 60 from the amount you added to make it saturated at 25. So 570 minus 410. 570 minus 410. Nice easy round numbers. 160 grams would be needed to be added to the solution at 25 degrees to make it saturated at 60 degrees.
So this one, 410 is dissolving is 570. Dissolving.
Well, the 410 grams of NaNO3 is dissolved in 456 grams of water.
Okay.
And then the water is heated up to 60 degrees Celsius. And you need to add 160 grams to make it saturated at 60 degrees, because at 60 degrees Celsius, the solution, the 456 grams of water can hold 570 grams of sodium nitrate. Does that make sense?
Mm-hmm. So the action is saturated.
Yes, it is. Well, in both cases, it's wanting to get to a saturated solution. So it's saying enough sodium nitrate's dissolved at 25 degrees to make a saturated solution. Well, we figured that out to be 410 grams. We needed to dissolve 410 grams of sodium nitrate to make it saturated at 25 degrees. And then it says how much more must be added to make a saturated solution at 60 degrees. So we calculated how much would be needed to be added at 60 degrees to make it saturated. So this is the amount to make it saturated at 60 degrees. This is the amount to make it saturated at 25 degrees. How much more do you need here? How much more do you need to add to this solution to make it saturated at 60? You just subtract and figure out it's 160 grams you have to add. Okay? Alright, so next. Now we're going to deal with some concentration problems. So what is the concentration in percent mass volume of 150 milliliters of solution containing 30 grams of solute? So in this case, we have to know what the equation is for calculating mass volume percent.
So it's 1 gram of salt or 1 liter of solution?
No, mass volume percent, or percent mass volume, is always the gram solute divided by the milliliters of solution.
Oh, milliliters, okay.
Times 100%. And mass percent is always the grams of solute divided by the grams of solution times 100%. And then the percent mass volume, actually we should make that a lowercase, huh? Or actually this is volume percent, sorry, volume percent is milliliters of solute over milliliters of solution times 100%. So in each of these cases, it's always divided by the solution. And in each of these cases, the mass is always represented in grams, and the volume is always represented in milliliters. So now what we can do is we can go ahead and calculate the mass volume percent concentration. So we're going to use this one for this particular problem. So it's going to be what? How would I set that up?
30
Uh-huh.
over 150.
30 grams of solute over 150 grams of solution. 150 milliliters of solution, I said.
And 0.2.
Times 100%. So you can't times it by 100%.
It's 20%.
Yeah, 20%. Now, strictly speaking, in this case, this is only one significant figure, so your answer would only have one significant figure, although, and generally speaking, you would have more than one significant figure as an answer to one of these questions. Alright, so now it says how many grams of NABR are needed to make 2.4 liters of a 12% mass volume sodium bromide solution.
Okay, you are looking for grams.
Yes.
First of all, we can put conversion at 12 over 100.
Yes, and that's an excellent way to start. So, anytime we're given a percent concentration, we can use it as a conversion factor. It's a 12% mass volume solution, and it's 12% NABR. Well, that means, percent means per 100, so I can actually change this into a conversion factor, and I can write it as 12 grams NABR over 100 milliliters of solution. Because that's what percent means, it means per 100. 12 grams per 100 milliliters. So with that as my conversion factor, I'm not going to start with this, I'm going to have to start with what?
We have to convert this down to 15.
Well, first what number do I have to start with?
30. No.
Problem number 8. What number do I have to start with?
12.
Nope, that's our conversion factor.
Yes, but we are looking for 2.4 liters.
We have to start with 2.4 liters.
Yes.
Yeah, we have to figure out how many grams of NABR are needed for 2.4 liters. But right now, since we have liters, we're not going to be able to use this conversion factor right away. What do we have to do with liters?
Milliliters.
Convert to milliliters. So liters is going to be converted to milliliters. 1,000 milliliters equals 1 liter. And then, from there, I can use this conversion factor and convert milliliters to grams rather. So milliliters, grams of NABR. So 100 milliliters of solution is going to give me 12 grams of NABR. And then I simply multiply by the top and divide by the bottom. And if I do that, I will get my answer.
And the answer is 2.4. Divide 100.
Close to 300, what?
288.
288? I was trying to do it in my head, but I couldn't do it fast enough. Your calculator's too fast for me. Alright, 288 grams of NABR. So now, that's how we deal with one of these percent concentration problems when we're given. When we're given the percent. Question number 9 says 20 grams of sodium nitrate is dissolved in 75.3 grams of water. What is the concentration of sodium nitrate in percent by mass? Okay, so for this question, we're going to use what equation?
We have here a graph, and we are looking for percentage mass over mass.
Yeah, so we're going to use this one, the mass percent calculation. So what's going to go on the top there? What's our mass of, what's our grams of solute?
Solute is 20.
20, yeah. 20.0 grams of solute, sodium nitrate, NaNO3. What's going to go on the bottom? 75.3? Actually not.
Hold on. Dissolving 75.3 gram or more.
Because remember, the equation is grams of solute over grams of solution.
But your water is not solution.
Water is not the solution. Water is only part of the solution. What's the other part of the solution? Solution.
Solution is a solute plus solution.
Solute plus solvent.
Solvent.
Yeah. Solution is the solute plus the solvent.
Yeah.
The water here, the 75.3 grams of water is just the solvent. What do I have to add to it to get the solution?
You have to add the 20.
Yeah, the 20.0. And NaNO3. So, I'm going to take 20 divided by 75.3 plus 20. So it's 20.0 grams of NaNO3 divided by 95.3 grams of solution.
95.3.
That's 100%.
So, without 100, I have 0.209.
Well, times it by 100.
Times 100?
Yeah.
20.98.
20 point what?
98.
98? Well, that means it's going to be 21.0%. Because this is 3 sig figs, this is 3 sig figs. So 21.0 mass percent of sodium nitrate. There you go. Now,
I didn't pay attention at that first.
yeah. So be careful with those because you will get, and you sometimes do get questions like that where it kind of tricks you a little bit. It gives you the water, but not the solution. And you have to remember that solution is equal to solute plus solvent. So if it says solution, then you can just put it on the bottom. But if it says a solvent, or if it says water, then that means you have to calculate the mass of the solution. Yep. Okay. So, number 10 says, concentrated HCl solution is about 35.3% by mass. How many grams would be needed to be bubbled into water to make 950 grams of total solution? And how much water would be needed? So this is once again a case where you're actually given the concentration. The concentration is 35.3% by mass. So if it's 35.3 percent, mass percent, HCl, then that basically means it's 35.3 grams of HCl for every 100 grams of solution. When you're given a concentration, use it as a conversion factor. Now in this case, what number am I going to start with? What amount am I going to start with?
So, first of all, you want to start with 950 grams?
Yep. I'm going to start with my 950 grams of solution. And then, since this has grams of solution as part of its part of this conversion factor, I'm going to put grams of solution down here. Just like I always do with conversion factors, the unit that was previously up here has to come down here to cancel out. And grams of HCl come on top. And it'll be 35.3 grams of HCl is equal to 100 grams of solution. I multiply the top and divide by the bottom. And that will give me
950. 33. 335.
335. Okay, 335 grams HCl. Okay, so now that is the amount, that is the mass of HCl that would need to be bubbled into it. Now how much water is needed?
How much water you needed?
So remember, we're making a 950.
So this one, your answer minus subtract the total.
Yeah, so I would take my 950 grams of water and I would subtract my 335. Right, this is 950 grams of solution rather, minus my 335 grams of solute HCl, and that's going to give me my grams of solvent, which in this case is going to be 615 grams of solvent or water. So I have my two answers here. I'll need 335 grams of HCl bubbled into 615 grams of water. Cool. So, now, let's take a look at some molarity problems. 11 says, what is the molarity of a solution made from dissolving 5 grams of NaOH in 750 milliliters of solution?
So, molarity is 1 mole of solute?
Well, molarity isn't...
Mole of solute over a liter of solute.
Moles of solute over liters of solution, that is right. So, molarity is moles solute over liters solution. Or in symbolic form, big M equals MOL over L. So, when you're solving for molarity, there's 3 basic steps. And the 3 basic steps are, step 1, solve for moles. Okay? Now if it gives you the moles, you don't have to worry about this step, but if it does not give you the moles, then you're going to have to convert the grams to moles. In this case, we're not given the moles, so we have to convert the 5.00 grams of NaOH to moles. Now, grams of NaOH is going to have to come on the bottom, and I'm going to have to put the moles of NaOH on top. Ideally, you already should know how to do this. I think you do. But what would be needed to convert grams to moles?
We have to find the mass of NaOH.
You find the molar mass of NaOH. And just in case anybody forgot how, sodium, there's 1 of them, and the mass is 22.99. Oxygen, there's one of those, and the mass is 16.00. Hydrogen, there's one of those, and the mass is 1.01. So multiply each of the atoms times its mass, and then add them all up. 22.99.
The answer is
That's going to give you 40.00, right?
oh, you put 40.00? Yeah.
And so it's going to be 40.00 grams per 1 mole. If you then divide the 5 grams by 40.00,
Is 0.
that's well,
125.
yeah, 0.125, right?
Yeah.
That's moles of NaOH. So first step completed. We have solved for moles. Step 2.
You have to convert the milliliters to liters?
Exactly. We solve for liters. Solve the volume in liters. So in this case, we're given 750 milliliters, 750.0 to be precise. And then we'll simply convert milliliters to liters, knowing that 1,000 milliliters is equal to 1 liter. And that gives us 0.7500 liters. So now we have our moles and we have our liters. That brings us to merry old step 3, which is
Dividing mole over liters.
divide moles by liters.
So you have
And so molarity is equal to moles over liters. You substitute in the moles, 0.125. Liters is 0.7500 liters. And if you divide the moles by the liters, you get what?
Because we have 3 significant.
Mhm.
Do we have 3 significant?
Yeah, 3 significant figures on top and 4 on bottom, so you go with the lesser
Three.
amount, 3.
So the answer is 0.167.
0.167.
0.167.
Molarity NaOH. Doo-doo-doo. Yay. And just for clarity's sake, clarity for the sake of charity, I will separate step 1, step 2, and step 3. Yay! Clear as crystal, right?
That's good.
Alright, so now we're going to go to number 12. It says how many moles of LiBr are needed to make 50 liters of a 1.25 molar LiBr solution.
So we have the molarity?
Yeah, in this case we're given the molarity, which means just like when we're given other concentrations, if we're given molarity, we can use it as a conversion factor. We can use it as a conversion factor. So, start with my molarity. I'm not actually going to start with my molarity, but I am going to want to identify how I can break it into a conversion factor. Since 1.25 molar LiBr is my concentration, I need to recognize that since molarity means moles per liter, that means 1.25 molar can be rewritten as 1.25 moles of LiBr per 1 liter of solution. Make sense? So molarity is moles per liter, so per 1 liter. So anytime I have molarity, I can rewrite it as a conversion factor. So now, since that's my conversion factor, I'm going to start with what number?
You want to start with 124?
You mean 50?
No.
Do you mean 50?
50?
50 liters, right?
You want to do from that way? Just I do just plug in.
Well, you could, okay, so there's two ways to do this. So I have 50 liters. I can use this as a conversion factor. I can just bring liters down here and moles of LIBR up here. See, with liters already given me, I can just use this as a conversion factor. 1 liter is 1.25 moles of LIBR. And if I multiply the top and divide by the bottom, I get 62.5 moles of LIBR. So I can do it like that. And that actually is, in many ways, a lot easier. You don't have to worry about rearranging an equation. Alternatively,
Easier.
if you wanted to, you could also use this as an equation. The molarity is given 1.25 molar, and that's equal to the moles, which is what you're looking for, divided by the liters, which is what you're given, 50.0 liters. And sure, you can solve for moles by just multiplying both sides by 50. And that's pretty easy too. Now let's take a look at number 13. It says how many grams of H2SO4 are needed to make 750 milliliters of a 2 molar solution. Once again, we're given molarity, which means we can use it as a conversion factor. Only this time, our molarity is 2 molar. It's 2.00 molar H2SO4. Notice we do want to include the substance when we write the concentration. And this can be rewritten as 2.00 moles H2SO4 per 1 liter. Now in this case then, once again I could do it one of two ways. I could go ahead and use the equation, or I could use that as a conversion factor. But there's a distinct advantage to using this as a conversion factor, because I'm not given liters here.
You can convert.
Yes, I can. So I can take 750.0, sorry. 750.0 milliliters, and I can convert milliliters to liters. 1,000 milliliters to 1 liter. Then, if I wanted to use the equation, I would say, okay, well that means I have 0.7500 liters, right? Now I can go ahead and use the molarity is equal to moles per liter equation. And that would give me 2.00 molarity is equal to an unknown number of moles per 0.7500 liters. I would then multiply both sides by 0.7500 liters, 0.7500 liters.
That is 1.5.
And then my moles
Is 1.5.
1.50 moles of H2SO4.
Oh, yeah, 3 significant. Okay.
Now here's the thing, it's asking me for grams of H2SO4, so I now have to do a separate step of taking my 1.50 grams of H2SO4 and converting it, grams of H2SO4, to moles of H2SO4. And of course, this is going to require me to find the molar mass. 1 mole is, in this case, if if you do the molar mass correctly, it's about 98.08, roughly. And 1.5. Oh, sorry, whoops, what am I doing? I messed this up. It's 1.50 moles of H2SO4, not grams. And I'm converting to grams. Yeah, I have it upside down. My bad. So 1.50 moles of H2SO4. Moles of H2SO4 is going to have to go on the bottom. And 1 mole is equal to 98.08 grams. So 1.5 times this.
So 1.50 times 98.
No.
That is 1127.
Huh?
1127.92.
Nope.
No.
1.5 times 98.08. That should be,
1.5
honestly,
times.
what's going down to 147.
Yeah, 98.08. Oh yeah, 147.12.
Now in this case, it only has 3 sig figs, so 147 is fine.
Yeah.
Now that's a lot of work for that particular problem. You could have solved this a little bit more quickly and a little bit more easily by not using the equation and instead using this as a conversion factor. And if I did that, it would look like this. I would start with my 750.0 milliliters, just like the other one, and I would convert the milliliters to liters. 1,000 milliliters is equal to 1 liter. But then with the liters, I can use my conversion factor here. So I can put 1 liter is equal to 2.00 moles of H2SO4. Then extend it a little bit further, and I can convert moles of H2SO4 to grams of H2SO4, and that's going to be 98.08. Grams is equal to 1 mole. And if you multiply everything on the top and divide by the bottom, you get 147 grams of H2SO4. Nice advantage of this one. You don't have to round in between the stages with regards to sig figs. And you streamline it into one process. And so you're less likely to make mistakes on, doing the algebra, less likely to make mistakes on like figuring out where to go from after you get the answer for here. So I do recommend that, but you can do the other way if you feel it's easier for you. Alright. That's most of the calculation-based stuff. The rest is pretty much concepts for solutions, things that we ought to know. So let's do a quick review of dissociation. So what does it mean to dissociate? Well, when substances dissolve in solution, they can dissociate or break down. Dissociate kind of means to separate from. Just like, for example, if you disassociate yourself from another person, that means you no longer spend time with them. It means you separate yourself from that person. Dissociate means the molecules or the particles separate from one another as well. Now, in the case of ionic compounds, this dissociation means they break apart into separate ions. In the case of covalent compounds or molecular compounds like sugar or things like that, then those will separate into molecules. So we're really going to be focused more on the dissociation of ionic compounds. So like in this case, NaOH. So the ions that make up NaOH are The ions that make up NaOH are the sodium ion and the hydroxide ion. Now sodium has a charge of what?
1.
+1. And hydroxide has a charge of -1. So sodium, when it's dissolved in water, will break up into Na plus ions and OH minus ions. This is the dissociation equation. You may be asked to write a dissociation equation for an ionic compound. Well, what about if you have an ionic compound like MgCl? And the little H2O on top, it's not reacting with it, it just means that you're dissolving it in water. So what will magnesium chloride separate into?
Mg and chloride.
So Mg with what charge?
Mg positive.
Positive 2. And what else will it break up into?
Cl, chloride.
Okay, so how do I write that?
2Cl.
2Cl, very good. They're separate chloride ions. It's not going to write as Cl2. I'm not going to write Cl with the subscript 2, but it's two separate Cl minus ions. So that would be the dissociation equation for magnesium chloride. Very good. Now, the only substances that will dissociate completely like this, when they dissociate completely, they are called strong electrolytes. Strong electrolytes dissociate completely. Completely separate into ions. Okay? Strong electrolytes completely separate into ions. Okay. So what kind of substances are strong electrolytes? Well, there's only two things that can be considered strong electrolytes. So examples of strong electrolytes would be any soluble ionic compound, and strong acids. Soluble ionic compounds and strong acids. So that would be like HCl, HBr, HI, and yes, unfortunately, you have to memorize the strong acids. So I'll list them out real briefly here. The strong acids, HCl.
This is the one he put on the website, on the slide 6. Like this. I will tell you what he did.
HCl3.
Yeah, HClO4, H2, SO4, HI, HBr, HCl, HNO3.
Yeah. So those are the only 7 strong acids. There are literally millions of weak bases, or weak acids rather.
Oh, ClO3, ClO4. Just give them put ClO3.
Yeah, ClO3 and ClO4, those are both going to be strong acids. So soluble ionic compounds and strong acids are strong electrolytes. Then there are what are known as weak electrolytes. And weak electrolytes they dissociate, but they only dissociate very partially, a little bit. Dissociate
With with a few ions and some molecules.
Yeah, dissociate only a small amount. Into ions. For weak electrolytes, most of the substance remains as molecules. Okay, so only a small amount into ions. So, what are some examples of weak electrolytes?
Like HCl?
H what?
HCl?
No, HCl
It's strong. Okay.
it's a strong.
Uh,
So weak electrolytes, I'm going to use the other marker because this one's almost dead. Weak electrolytes, some examples include
NH4.
yes, weak acids and weak bases. So weak acids and weak bases. I guess it's not, those are categories, not really examples, but examples would be like HC2H3O2 and NH4 plus, or NH3 even. NH3 is a weak base, a nitrogenous base. The nitrogen hydrogen compounds are weak bases, and any acid that's not one of the 7 strong acids I listed is going to be a weak acid.
Mm-hmm.
And you can typically tell weak acids because they usually have an H thrown in front of them. Alright. And then, last but not least, we have the non-electrolytes. So there's the non-electrolytes. And non-electrolytes would be anything that dissociates only into molecules. It doesn't dissociate into ions. It doesn't separate into ions. It dissociates only into molecules. Now it's possible I could be using the term dissociate improperly, but I don't think so. It separates only into molecules, but it does not dissociate into ions. So, no ions. And because there's no ions, it's not an electrolyte. It's not something that can conduct electricity. And therefore, examples of non-electrolytes would typically be any molecular compound that's not a weak acid or base. So this would be something like
any kinds of sugar?
Yeah. So it'd be like sugars,
And alcohol?
alcohols, yep. Sugars, alcohols, things of that sort. Those are going to be your non-electrolytes. Okay, so looking at that, let's identify the non-electrolytes. Let's identify the electrolytes as either being weak or strong or non. So, acetic acid. Oh, is it okay if I erase this?
Yeah, you can.
Okay. I'll at least erase the top part.
Uh-huh.
So, acetic acid, HC2H3O2, is that a weak electrolyte, a strong electrolyte, or a non-electrolyte?
It is, I think, weaker.
Yeah, this is weak. It's an acid, but it's not a strong acid, so this is a weak electrolyte. Oops. Now, what about 17, which is, well, I have two 17s. What about 17 sodium iodide? What about sodium iodide?
A strong electrolyte?
Yeah, that's an ionic compound and it's soluble, so that's going to be strong. What about glucose?
This is non-electrolyte?
Yeah, glucose is a sugar. It doesn't separate into ions at all. It's going to be a non-electrolyte.
And HF is a strong.
HF. Actually, HF is weak.
Weak.
HF is not, it's an
It's
acid.
a
but
strong
it's-
acid, but it's a
It's
weak
not-
electrolyte.
Well, no, it's not a strong acid. HF is a weak acid.
Oh, yeah.
It's not one of those sevens. So this is a weak acid, and therefore it is a weak
Weak electrolyte.
electrolyte. And then, if you look at those two equations below, identify each one classified as strong, weak, or non-electrolyte. What do you think? Number 19.
19?
Yeah.
Strong. For this formation, which one is it?
Is it-
Strong?
is
Okay,
it-
that's 19 is a strong.
It's a strong electrolyte.
Yes, and HNO3 is a strong acid. Is a strong acid,
Yeah.
but it is weak.
Nope, it's a strong electrolyte. Strong acids and ionic compounds. Strong acids and ionic compounds.
Yeah.
They're both strong electrolytes. So 19 and 10 are both. Now, in general, if you see any substance like this, any AB, and the arrow is one directional,
This is, I know that this is a strong electrolyte.
this is going to be a strong electrolyte.
But whenever you have two arrow, is weak electrolyte.
Exactly. So if you had CD, and it looked like that, C plus and D minus, that's going to be a weak electrolyte.
Oh, you're right. It was a good trick. I didn't pay attention to arrow. Yeah.
All right. So now the last bit is equivalence. It says determine the number of equivalents in each of the following quantities. So an equivalent refers to a mole of electrical charge. So in this case,
Oh,
an equivalent is a mole of electrical.
equivalent is only on.
I'm sorry?
It's not on.
Well, we're going to go over it anyway.
Yeah,
So 2.4
we have to do that.
2.4 moles of magnesium, Mg2+. So equivalent to the mole of electrical charge. So what's the charge of magnesium 2+? It's 2+, right? So the total number of moles of electrical charge is going to be 2.4 moles times 2. So this is actually 4.8 equivalents. Pretty easy, right?
Yeah.
And so if I have 0.75 moles of aluminum, Al3+, that means that I have how many equivalents?
3
Not 3. 0.75 times 3.
times 3.
Yes.
So the answer is
2.25 equivalents.
good.
Or 2.3 with 2 sig figs. Now if I had something like 24, it says 3.87 grams of sulfate.
87 times 2 is 7.74.
Well, actually not quite.
Oh yeah, you know what? That is not.
So, in the case of the 3.87 grams of sulfate, if I'm trying to figure out the equivalence there, I need the moles first before I can calculate that. So what I would do is I would take my 3.87 grams of sulfate, SO4 2-, and I'd actually have to convert the grams of sulfate, SO4 2-, to moles of sulfate. Now, the molar mass of sulfate is 96.06. That's the grams per 1 mole. And if I calculate that, what does that give me? 3.87 divided by 96.06?
3.87. 0.040.
Should I have one more sheet, baby?
2.
That's moles of sulfate, SO42 minus. Now, since that's the moles of sulfate, the equivalence here, I would simply multiply the moles by the charge, which is 2, and so I would have 0.0804 equivalents. And so that's how you do calculation of equivalence. Well, I hope that helped, and thank you for coming.
Thank you so much for coming.